Welcome to the last sequel of the Apollonian spider. In the final part of this series, it is time to reveal the hidden mathematical structure that lies underneath fractals of this kind. You will encounter a beautiful piece of group theory, a part of mathematics that ubiquitously permeates almost all of math and physics. So let's dive right into it. We have already identified the role of the two complex transformations A and B, and we've seen that they can be represented by complex 2x2 matrices that are elements of the special linear group, which just means that the determinant is equal to 1. This property is preserved no matter how often these matrices get multiplied with each other. The two matrices will generate a subgroup of the group of all special linear matrices, and this subgroup will be intimately related to the Apollonian gasket. Before we start with the full picture, it will be instructive to first consider two simpler matrices with real-valued entries. Take, for instance, the matrices A and B in the following form. With this simpler version, it is easily possible to refresh or introduce some ideas of the structure that is simply called group by mathematicians. All elements of the group can be generated systematically. One starts with the 2x2 unit matrix and arranges the elements inside a tree. Stepping down to the left means that the parent element, here the identity matrix, is multiplied by A from the left, and stepping down into the right branch means that the element at the node is multiplied by B. The multiplication from the left seems a bit awkward at first glance. However, matrices are quite often interpreted as linear maps. In such a case, matrices ordinarily act on column vectors, and this action is naturally defined as a multiplication from the left. Each element of the group can be labeled by a word that solely consists of the letters A and B. The words grow from right to left, and the tree is shown here up to the third level. In a second tree, the corresponding matrices are displayed. It turns out that the element labeled with AA is equal to the unit matrix. Therefore, we disclose the relation A squared is equal to unit T. It can be used to simplify some words. Every occurrence of two consecutive letters A can be cancelled. Some parts of the tree will just be copies of previous parts, and they can be removed as well. The same repeats when the group element BB is considered. B also is its own inverse and squares to the unit element of the group, and the tree simplifies accordingly. Another interesting property is that the word AB differs from the word BA. A group with such a property is called non-commutative. The group shown here is in fact the smallest non-commutative group that exists. In the third level, one finds yet another relationship that BAB is equal to ABA. All relations can be summarized in one line, and they are the defining relations for the dihedral group of order 3. This group can be understood as the symmetry group of an equilateral triangle. When the matrices A and B are interpreted as linear maps, A reflects the triangle vertically and B reflects the triangle along a line of symmetry which is rotated by 60 degrees. This group is also isomorphic to the permutation group of 3 elements, as indicated by the labels on the corners of the triangle. The relations on the generators A and B are the reason for the group to only consist of 6 elements. These kind of finite discrete groups are usually studied first, and a lot of viewers will certainly be familiar with finite groups. You may also have realized that the determinant of A and B is not equal to 1, but minus 1 instead. Therefore, this generated group is not a subgroup of the special linear group. In fact, it is a subgroup of the orthogonal group, which means that all distances and angles are preserved by the corresponding linear transformations. When we now turn back to the two generators A and B that create the Apollonian gasket, The group structure will show a few similar and a few distinct features. First, again, group elements will be arranged in a tree, and each element will be labeled by a word. But now A and B are not their own inverses, and the inverse transformations A and B have to be included in the construction of the tree to generate every single element of the group. The only relations that can simplify words are products of a matrix with its inverse. We can avoid the occurrence of these latter combinations when the tree is only extended by the three generators that do not contain the inverse of the element at the parent node. For later convenience, the same letter is always followed by the same three elements in a cyclic order. It turns out that there are no further relations that simplify the words in the tree. Each matrix is different. Such a group is called a free group. Therefore, this tree continues forever and there are infinitely many elements generated by the two generators A and B and their inverses. Unlike before, the matrices A and B are not interpreted as linear maps, but as Möbius transformations instead. The dihedral group was used to transform the equilateral triangle into any of its possible symmetric configurations. The group generated by the two Möbius transformations can be used to map some fundamental region of the complex plane into any other region of the complex plane. The fundamental domain is shown here in white, first as a projection onto the Riemann sphere, and then as the lower half plane with three disks removed. When all group elements of the group are applied to this fundamental domain, every part of the complex plane is covered exactly once. This fact is illustrated by the next animation. First, the fundamental domain is transformed by the two generators A and B and their inverses. We recover the disk-like structures that are familiar from earlier videos. Remember, although the gray area corresponds to the full upper half plane, it also can be considered as a disk with infinite radius. Similar to the fundamental domain, each disk contains three holes. When now all the 12 two-letter words are applied to the fundamental domain, which is equivalent to transforming the images, again with the generators and their inverses, all the 12 holes will be filled with new disks containing a total of 36 holes. It comes to no surprise that these holes will be filled by the 36 group elements of the next level in the tree, leaving 108 new holes behind. And the story of course continues as long as you wish. Let me tell you a few words about the imperfections in this animation. Unlike in the simplified model without holes, the fundamental domain is modeled as a mesh object. Practically, it cannot be modeled as an infinite disk. Instead, it is modeled as a disk with a very large radius. The little bulges and indentations on the edges of the image disks indicate this artificial cutoff to infinity. This way, you can get a feeling of how crazily these maps transform the original fundamental domain. Hopefully, you don't mind the slight simplification to forget about all the holes and return to the picture of the full disks. From a group theoretical point of view, it was necessary to identify the fundamental domain, which is the pre-image of all the disks that show up in the animations. The disks are geometric representations of the group elements. Moreover, from now on, only the new letter is displayed in the group tree, so the full word is always recovered by concatenating all letters from right to left, while you walk along the branch from the identity to the node under consideration. The picture is repeated and extended for a few more levels. The disks shrink towards the Apollonian gasket. Consequently, the most interesting elements of this group for our purposes are words with infinitely many letters. Each of these words transforms the fundamental domain into a single point. The set of all these points is called the limit set of the group. It turns out that the Apollonian gasket exactly corresponds to this limit set. But still the order of the appearance of the disks seems rather arbitrary. Now everything is prepared to explain how the points for the fractal can be generated in the correct order. Please note that it appears to be very tedious to shrink all these disks to zero size. Some of them seem to decrease only very slowly. In fact, there is an easier way to locate all the points of the limit set. Therefore, we need to return to the fixed points of the Möbius transformations. We have seen that these fixed points can be calculated. In general, there are two of them, and one is attractive for the transformation and the other one is attractive for the inverse transformation. In fact, each of the fixed points corresponds to an infinitely long word consisting of the same letter. For instance, all letters A or all letters A. Every point in a complex plane, except z equal to -1, will be mapped to 1 when the transformation A is applied repeatedly forever. Similarly, every point in the complex plane except z equal to 1 will be mapped to -1 when the inverse transformation A is applied infinitely many times. When the fixed points of the transformations A and B for the Apollonian gasket are calculated, one finds that both of them only have one single fixed point. This is easily derived from a few lines of algebra. One has to ask which complex number z is mapped onto itself when the transformation A is applied. This gives rise to a quadratic equation with just one solution. The fixed point nicely reveals itself in the transformation of polar grid lines, when the center of the origin is located at the fixed point. This also means that the transformation and its inverse tend towards the same fixed point. This is the reason why always three circles touch each other in the Apollonian gasket in comparison to other Kleinian fractals. There is a fast way to distinguish whether a Möbius transformation has one or two fixed points. Let's start with a general normalized Möbius transformation. The fixed point equation for this Möbius transformation takes the following form. The solution of the corresponding quadratic equation is written down by the well-known formula. The condition for a single fixed point translates into a vanishing discriminant underneath the square root. This condition further simplifies with the assumption of normalization. When the Möbius transformation is represented by a matrix, the sum of the parameters A and D is usually referred to as the trace of the matrix. Consequently, the condition for just one single fixed point reduces to the statement that the trace of the matrix must be plus or minus 2. This condition is certainly satisfied by our transformations A and B. Let's return to the tree and have a look how this tree can be extended to infinity. We can see that the node A is normally followed by the node B, A and B. In order to be able to extend the tree without increasing the complexity, we just consider the left and the right branch. Therefore, only B and small b are added. Now B would normally be extended by A, B and A. Here we only keep the leftmost letter A. Similarly, B would be extended by small b and A. We only keep the rightmost node A. Next, when we look at the branching of A, it is extended by small b to the left and B to the right. At each new level, the left branch is extended with the corresponding leftmost node and the right branch with its rightmost node. After 4 levels, the pattern of letters repeats and is easily extended to infinity. These steps are repeated for all leaves of the original tree. For the rest of this discussion, we will look at the group tree from another perspective. Instead of starting with the fundamental domain and transforming it to smaller and smaller disks, we now start at the end of such an infinitely long extended branch. For example, take the one highlighted in yellow. There are infinitely many repetitions of the pattern BA and small ba. The matrix representation of this pattern is readily computed. Its determinant is 1 and its trace is -2. This group element is called a commutator. It would be equal to the identity matrix for a commuting group. Therefore, it is a measure of the amount of non-commutativity. Its trace is -2. Therefore, there's only one fixed point associated with it, which is denoted with F1. Any domain or any complex number is mapped to this fixed point once the pattern has been applied infinitely often. Therefore, the entire highlighted part of the branch can be replaced by its fixed point, and the rest of the branch is acting on this fixed point. The result of this action will be a part of the Apollonian gasket, since it corresponds to an infinitely long word. In the next branch, there is the repeating pattern of small b, capital A, B, and small a. The story repeats. This time there is a fixed point denoted by F2. Then the third branch is replaced by the fixed point of the pattern small a, capital B, A, small b, which is labeled with F3. The fourth branch is completed with the repeating pattern capital AB, small ab, which is the inverse of the first commutator. Therefore, the branch is again replaced by F1, since there is only one single fixed point for each commutator and its inverse. In general, one would end up with different fixed points for the commutator and its inverse. In the case of the Apollonian gasket, only 4 different fixed points have to be considered. The next 4 branches repeat, and then the last fixed point F4 appears at the parent node capital A. The procedure is extended to the entire tree. Finally, the transformations along each branch are applied to the fixed points, and the resulting images are shown in the complex plane. For the example, first the matrices along the branch, here small a and capital B, are multiplied with each other. The resulting matrix is applied as a Möbius transformation to the fixed point F2, and the image is plotted in the complex plane. As you can see, only 12 points emerge from the 24 leaves of the tree. The right leaf of one branch always coincides with the left leaf of the neighboring branch. Moreover, most importantly, the points appear in the correct order when the tree is evaluated branch by branch. To see this more clearly, the animation is repeated for a tree with one more level of group elements. Once the tree is built up to the third level, the corresponding left and right fixed points are added again. In the end, there will be 72 leaves that give rise to 36 elements of the limit set that are shown in the complex plane. The picture is completed with the Apollonian gasket that corresponds to an evaluation of the tree at a much deeper level. If the tree was extended to infinity, this blue curve would show repeated circular patterns at every scale. No matter how far you zoom into the region of the curve, smaller and smaller circles would show up. Let's wrap up with a simple Python implementation. In a first class, the model parameters are specified. The generators and their inverses are stored as NumPy arrays. In a dictionary, labels and generators are linked with each other. A second dictionary stores the corresponding left and right fixed point values for each of the labels. The function nextLabel is crucial for building the tree in the same way as it was shown in the animation before. If the parent node is the identity, all generators are added as children in the order of their appearance in the label list. Once the node for B is generated, the function will return none to indicate that the construction of the first level is finished. For all other levels, only 3 out of 4 generators are added as children to each parent. The inverse generator is omitted, and the function ensures that the nodes are always added in the same cyclic order. Don't worry about the details. The modular operations that show up in the code just constrain the index to always stay between 0 and 3. Most likely this could be implemented much more skillfully and more efficiently. The class node is an extension of an existing Python package AnyTree. It is equipped with the possibility to define parents and children and build the tree accordingly. Additionally, each node stores its label and a value that is a 2x2 matrix, which represents the product of the corresponding generator with all the matrices from the parent node, grandparent node, and so on. The class freeGroupTree is the place of number crunching. Here the full group tree is built level by level. The user can specify the size of the tree when a concrete object of this class is constructed. The nodes of the last level are all collected in the list leaves. The class contains a single function, getPoints. In this function, the value of each leaf is applied as a Möbius transformation to its left fixed point. Since the right fixed point of the previous branch gives the same result, one can restrict the computations to the left fixed points. However, in a more sophisticated algorithm, one could adaptively go to deeper levels of the tree depending on the separation of the images for the left and right fixed point of one branch. For simplicity, this is omitted here, which leads to plots that do not have the same resolution everywhere. One big advantage of Python is that it more or less automatically can deal with the multiplication of matrices and the calculation with complex numbers. The list of complex valued points is easily plotted as shown in the last code snippet. And that's it. Here is a quick reminder of the topics that we have touched upon while we unraveled the secrets of the Apollonian spider. I hope you can share a bit of my fascination for the secrets that can be uncovered with complex numbers and a few simple transformations. If you got interested, you should have a closer look at the book Intra's Pearls, which inspired the presented journey of the Apollonian spider. The book gives a very detailed step-by-step instruction and more in-depth implementation details. The Apollonian gasket is embedded into a broader class of Kleinian fractals. It is kept simple for most of the time and should be understandable for high school students with only little experience in writing computer programs. Thanks for your attention. As always, leave your ideas and recommendations in the comments. All the best. Hope to see you next time. Bye bye.